Here's something most people don't realize. Right now, in 2025, there are more active Mars missions operating on the planet's surface than there were satellites orbiting Earth in 1960. We've quietly crossed a threshold. Mars has stopped being a destination for occasional visits and started becoming a place where humanity maintains permanent presence, even if that presence is robotic. This shift happened so gradually that nobody rang a bell. Before we start, a quick roll call. Write in the comments which part of this planet you're watching from, and then just listen and enjoy. So here's the central question. Why will humans build the first permanent colony on Mars, specifically by 2060? Not 2080, not 2100, not someday. Why that particular year? And what makes this prediction different from decades of science fiction promises that never materialized? By the end of this video, we'll understand three things. First, why the technological pieces are converging right now in a way they never have before. Second, what timeline the major space organizations are actually following, with real dates and real hardware. Third, why 2060 represents not just a guess, but a calculated convergence point of multiple independent factors. Let's start with what's actually happening. In September 2016, Elon Musk stood before the International Astronautical Congress in Guadalajara, Mexico, and announced SpaceX's plan to establish a Mars settlement supporting up to 1 million people by the 2060s. The presentation was watched by over 100,000 people streaming online. At the time, it sounded like typical Silicon Valley hyperbole, the kind of thing entrepreneurs say to generate excitement. 9 years later, in 2025, that timeline looks different. Not because it's guaranteed to happen, but because every intermediate milestone Musk described is either completed or visibly in progress. SpaceX's Starship, the vehicle designed specifically for Mars missions, reached orbital trajectory for the first time in 2024. Both stages achieved controlled splashdown, proving the basic across multiple generations. That's the definition we're working with. 3 major space programs are converging on Mars with overlapping timelines. SpaceX plans its first crewed mission as early as 2029, just 4 years after successful landing demonstrations. The mission would involve approximately 12 people tasked with building what they're calling Mars Base Alpha, establishing propellant production facilities and setting up power systems. NASA has committed to advancing 6 key technologies specifically for Mars human missions, including entry, descent, and landing systems designed for heavier payloads than any previous Mars landing. China announced plans to send crews to Mars orbit by 2050, with surface missions to follow. These aren't competing programs. They're parallel development tracks that validate each other's assumptions. When 3 independent organizations with different political systems, funding models, and engineering cultures all arrive at similar timelines, that convergence tells us something real about the underlying constraints and possibilities. Here's the scaling plan SpaceX has outlined, and this is where things get interesting. If the 2026 uncrewed missions successfully demonstrate reliable landing, SpaceX projects approximately 5 ships in the 2026 window, 20 ships in the 2028 window, 100 ships in 2030, and up to 500 ships by the 2033 launch window. This isn't linear growth, it's exponential. It mirrors how airline manufacturing scaled in the 1950s, once the basic jet engine design was proven. Each Starship is designed to carry over 100 passengers, with a transit time of 80 to 150 days, depending on the specific trajectory chosen. The program aims to eventually send 1 million people to Mars, using approximately 1,000 Starships launched during multiple Mars windows. The math works out to thousands of launches over decades.
Fuel production. You'd need to carry all return fuel from Earth, which makes the mass equation impossible. With it, Mars becomes reachable. So why 2060 specifically? Because that's approximately 35 years from now. And when you map out the development timeline, that's where self-sustaining settlement becomes feasible. The first decade, 2026 to 2036, establishes robotic infrastructure. The second decade, 2029 to 2040, brings the first 100 humans who build Mars Base Alpha. The third decade, 2040 to 2050, scales from outpost to town, with thousands of residents. The fourth decade, 2050 to 2060, achieves the critical mass of population, industry and agriculture necessary for the settlement to survive without constant resupply from Earth. Musk stated in 2024 that a Mars colony would need to develop self-sufficiency within 7 to 9 years of serious colonization beginning. That timeline refers to the settlement's ability to produce its own food, water, oxygen, shelter and basic manufacturing without Earth support. 7 to 9 years is aggressive but not impossible. It's roughly how long it took early American colonies to transition from total dependence on supply ships to basic self-sufficiency. We're living through something that happens maybe once every few centuries. A moment when humanity's technological capability, economic resources, and collective will align to make expansion into a new domain possible. It happened when humans first crossed oceans, when we settled remote islands, when we built cities in deserts and on coastlines. Each time, people wondered why anyone would leave comfortable, established places to go somewhere harder. And each time, enough people went anyway. The difference this time is consciousness. Previous expansions happened gradually, with settlers barely aware they were part of a larger pattern. We know exactly what we're attempting. We can see the whole timeline, debate the ethics, calculate the risk there permanently without constant support from Earth. And the engineering consensus across SpaceX, NASA, ESA and independent researchers is converging on yes, probably, if we solve about 15 major technical problems and 50 smaller ones. That's not certainty, but it's enough to proceed. So here's where we are. Hardware is flying, budgets are allocated, international timelines are synchronized, the chemistry works,
the orbital mechanics are favorable for the next several decades. The economic model, while aggressive, isn't physically impossible. We're not waiting for new physics or miraculous inventions. We're engineering with known principles. The invisible moment we're living through is this: Mars has transitioned from someday to 2060. That's a date close enough that people making career decisions today will live to see whether it happens. Close enough that current policy decisions matter. Close enough to plan for, invest in, and prepare for. Far enough that we have time to get it right. Space travel looks magical from Earth. Rockets rise on pillars of fire, pierce clouds, and vanish into darkness. But beyond the atmosphere, everything becomes mathematics. Cold, inflexible equations that don't negotiate or compromise. Getting to Mars isn't about courage or determination. It's about orbital mechanics, energy requirements, and mass ratios. Understanding why 2060 is realistic requires understanding these numbers first. Let's start with the most fundamental constraint: transfer windows. Earth and Mars orbit the Sun at different speeds. Earth completes one orbit every 365 days. Mars takes 687 days. Because of this difference, the planets align favorably for travel only periodically. Every 26 months, Mars and Earth reach positions where spacecraft can make the journey using the least amount of fuel. This window stays open for several weeks, then closes for another 2 years. Miss your launch date, and you're away. At its farthest, 401 million kilometers. The distance varies so dramatically that mission planning must account for which part of the 26-month cycle you're launching in. Some windows are substantially better than others. Now, let's talk about the vehicle. SpaceX's Starship is designed specifically for this journey. It stands nearly 400 feet tall when fully stacked, making it the largest rocket system ever built. The vehicle consists of 2 stages: a booster called Super Heavy and an upper stage called Starship. Both are designed to be fully reusable. Reusability is the entire game. Every rocket before Starship has been essentially thrown away after one flight. Building a new rocket for every mission costs tens to hundreds of millions of dollars. If you can land the rocket, refurbish it, and fly it again, costs drop by orders of magnitude. SpaceX has proven this concept with their Falcon 9 rocket, which has now flown individual boosters over 20 times. Starship achieved a major milestone in 2024. On its 3rd test flight, the vehicle reached its desired orbital trajectory for the first time. On the 4th test flight, both stages achieved controlled splashdown after launch. This proved the basic design works. The engineering is sound. Now it's about refinement and reliability. In September 2024, SpaceX announced plans to launch 5 uncrewed Starship missions to Mars in 2026. These missions serve one purpose: demonstrate that starships can land intact on Mars. Landing on Mars is substantially harder than landing on Earth or even the Moon. Mars has an atmosphere thick enough to create heat during entry, but too thin to slow a spacecraft effectively with parachutes alone. You need powered descent, firing engines against the surface while computers manage descent rate in real time. The 5-ship 2026 mission plan isn't conservative, it's statistical. Send 5 ships for all critical infrastructure. The mass budget is unforgiving. Every kilogram launched from Earth costs fuel. Starship's payload capacity to Mars is approximately 100 to 150 metric tons per flight, depending on the specific mission profile. For perspective, that's roughly the weight of 2 fully loaded semi-trucks. Sounds substantial until you realize a single person requires about 10,000 to 20,000 watts of continuous power just for food production in a closed system. This is where in-situ resource utilization becomes non-negotiable. You cannot build a colony by shipping everything from Earth. The mass requirements become impossible. But Mars has resources, if you know how to extract them. Mars's atmosphere is 95% carbon dioxide. Subsurface ice has been confirmed by multiple landers and orbiters, particularly near the poles, but also at mid-latitudes. The Sabatier reaction is a well-understood chemical process that combines carbon dioxide and hydrogen to produce methane and water. Add electrolysis to split water into hydrogen and oxygen, and you can produce rocket fuel entirely from Martian resources. This is the closed loop that makes Mars reachable. Ships launch from Earth fully fueled. They land on Mars nearly empty. Robotic systems extract water from ice, split it into hydrogen and oxygen, capture atmospheric CO2, run the Sabatier reaction to produce methane, and refill the ship's tanks over several months. The ship then returns to Earth with fuel produced entirely on Mars. Without this capability, you'd need to launch from Earth carrying all return fuel, which approximately doubles the mass you're lifting out of Earth's gravity well. The math doesn't work. The fuel required to lift the fuel makes the problem exponentially harder. Local fuel production is what transforms Mars from theoretically reachable to practically colonizable. The energy requires gravity. This has never been done at this scale. If orbital refueling fails, the entire Mars timeline shifts by 2 years minimum. This uncertainty is built into all space programs. NASA's Artemis program to return humans to the Moon has shifted timelines multiple times. China's lunar base plans have adjusted as technology development revealed challenges. SpaceX is unusual not because they face delays, but because they communicate timelines publicly and accept the reputational risk when schedules slip. What makes the 2060 timeline credible isn't that every milestone will hit on schedule. It's that the underlying math works. The energy requirements are steep but achievable. The transfer windows are predictable. The resource extraction is chemistry, not speculation. The vehicle design has flown, even if it hasn't flown reliably yet. Compare this to fusion power or quantum computing. Those technologies face fundamental physics questions that remain unresolved. Mars colonization faces engineering questions. Engineering is expensive and time-consuming, but it's solvable through iteration. Build, test, fail, learn, rebuild. SpaceX has demonstrated this cycle works. Starship prototypes have exploded spectacularly, and each failure generated data that improved subsequent designs. The cost equation is the final piece. Current technology would price a Mars journey at roughly $10 billion per person. That's not colonization. That's a few government astronauts maximum. SpaceX's reusability approach targets around $200,000 per person once the system matures and launch cadence increases. $200,000 is expensive, but accessible. It's comparable to what European immigrants paid in inflation-adjusted terms to sail to America in the early 20th century. Not cheap, but within reach for someone committed to going. Perhaps financed through future labor contracts or skills-based sponsorship programs. The path from $10 billion to $200,000,
thousands of smaller problems. The equation balances if we solve them. It collapses if we don't.
That's what makes the next 35 years decisive. Taxation. There's a rule in space exploration that nobody talks about enough. Robots must arrive before people. Always. This isn't caution or conservative planning. It's survival mathematics. Humans require food, water, breathable air, temperature control, radiation shielding, medical equipment, and waste processing from the moment they arrive. Robots require none of these things. They can wait decades in frozen hibernation if necessary. The decade from 2026 to 2036 will be remembered as the robotic construction phase. This is when machines build the infrastructure that makes human presence possible. No press conferences, no heroic moments, just patient, methodical work by automated systems establishing the foundations of Mars Base Alpha. Here's what needs to exist before the first humans land. Habitats with radiation shielding, power generation systems producing continuous electricity, water extraction facilities pulling ice from subsurface deposits and processing it into potable water, oxygen production, separating water into hydrogen and oxygen, propellant plants, combining atmospheric carbon dioxide with hydrogen to synthesize methane fuel, food storage facilities, communications arrays, maintaining contact with Earth, backup systems for all critical infrastructure. None of this happens overnight. Each system must be tested, debugged, and proven reliable under Martian conditions. Dust gets into everything. Temperature swings from minus 125 degrees Celsius at night to 20 degrees Celsius in equatorial daytime. Dust storms can last months. Solar panels accumulate dust that reduces power output. Seals crack in extreme cold. Electronics fail from radiation exposure. Everything designed for Earth must be redesigned for Mars. The first uncrewed starships launching in 2026 carry the initial equipment.
Reactors to provide continuous power independent of sunlight. Larger propellant production plants with greater capacity. Excavation equipment to dig subsurface habitats and 3D printing systems designed to build structures from Martian regolith. Regolith is everywhere on Mars. It's the dusty, rocky material covering the surface, composed of silicates, iron oxides, and other minerals. Engineers have discovered you can mix regolith with small amounts of water or polymer binders and use it as construction material. It's not ideal, but it's local. Every kilogram of building material sourced from Mars is one less kilogram launched from Earth. The European Space Agency has developed concepts for swarm robotics on Mars. Instead of one large, complex rover, imagine dozens of smaller, autonomous robots working in coordination. Each robot performs simple tasks: excavate regolith, transport material, compact it into forms, repeat. Individually, they're limited, but collectively they can construct large structures. The system is resilient because losing one robot doesn't stop the project. The swarm adapts and continues. These robots use artificial intelligence, not for consciousness, but for decision making. They identify obstacles, plan routes around them, adjust excavation patterns when they hit hard rock, and coordinate with other robots to avoid collisions. The AI doesn't need to be sophisticated. It needs to be reliable. A robot that works slowly but never fails is more valuable than one that works fast but requires human intervention to fix problems. Underground construction solves Mars's biggest habitability problem: radiation. Earth's magnetic field deflects most cosmic radiation and solar particle events. Mars has no significant magnetic field. Surface exposure to radiation is roughly 100 times higher than Earth. Staying on the surface long-term in oxidizer. Hydrogen is combined with atmospheric carbon dioxide in the Sabatier reaction to produce methane fuel and additional water. The water produced by the Sabatier reaction is then split again through electrolysis, creating a closed loop that continuously produces fuel. The Sabatier reaction isn't speculative technology. It was discovered in 1897 and has been used industrially for over a century. The International Space Station uses a version of it to recycle carbon dioxide from crew exhalation into water. On Mars, you're running the same process at larger scale, with readily available feedstocks. The chemistry is proven, but scaling up is the challenge.
The Sabatier reactor on ISS processes the CO2 from 6 people. Mars propellant production needs to process tons of CO2 per day to refuel a Starship over several months. The reactors must be larger, run continuously without maintenance, and operate reliably in Martian dust and temperature extremes. This is why the first decade tests these systems without human lives depending on them. Power is the constraint underlying everything. Water extraction requires power to drill and heat ice. Electrolysis requires power to split water molecules. The Sabatier reaction requires power to run compressors and heaters. Habitat temperature control requires power. Communications require power. A single human requires approximately 10,000 to 20,000 watts of continuous power just for food production systems in closed-loop life support, not counting other needs. Solar power on Mars receives 43% of the intensity available on Earth. A solar array producing 100 kilowatts on Earth produces 43 kilowatts on Mars under ideal conditions. Factor in dust accumulation and actual output drops further. Dust storms can reduce solar output to near zero for weeks.
Communicate with satellites in Mars orbit, which then relay signals to Earth. This allows continuous communication even when Mars's rotation puts a base on the far side of the planet from Earth. SpaceX and other organizations plan to deploy these relay satellites during early, uncrewed missions. By 2029, if everything proceeds optimally, robotic systems will have operated on Mars for at least one full Earth-Mars cycle. They've extracted water, produced oxygen and methane, charged batteries through solar arrays, withstood dust storms, and demonstrated that critical systems function reliably. Ground control teams on Earth have learned how to operate these systems remotely, despite communication delays. Backup systems have been tested. Redundancies are in place. Only then does sending humans become defensible. Not safe, defensible. Space exploration is never truly safe. But there's a difference between calculated risk and recklessness. Sending people to Mars without proven infrastructure is recklessness. Sending them after years of robotic preparation is calculated risk. The first crewed mission will likely consist of approximately 12 people. These aren't tourists or politicians. They're engineers, technicians, and specialists whose job is to troubleshoot the systems that robots built. Robots can follow instructions, but when unexpected problems emerge, humans excel at improvisation. A seal fails on a habitat airlock. A solar panel array develops an intermittent electrical fault. A water pump cavitates due to unexpected mineral content. These are problems requiring on-site diagnosis and creative solutions. The crew's mission during their initial stay, probably lasting about 2 years until the next return window,
is to verify that everything works as designed, repair what doesn't, expand capacity where needed, and document everything for the next crew. They're not colonists yet. They're the construction team making sure the foundation is solid.
Plants are functioning, if habitats are sealed and pressurized, if water extraction continues reliably, then humans can justify the risk of going. Not because Mars is safe, but because the infrastructure exists to keep them alive. SpaceX's timeline projects the first crewed mission as early as 2029. This isn't a flags and footprints visit. The crew isn't coming home after a few weeks. They're staying for approximately 2 years, the minimum time required before Earth and Mars align again for efficient return trajectories. This duration fundamentally changes mission psychology. You're not visiting Mars, you're living there. The crew size matters. Current projections suggest approximately 12 people for this initial mission. That number isn't arbitrary. It's large enough to provide skill redundancy. If one person falls ill or gets injured, others can cover their specialties. It's small enough to fit aboard 1 or 2 starships with all necessary supplies. And it's psychologically viable for extended isolation. Research from Antarctica bases and submarine crews suggests groups smaller than 8 experience dangerous isolation effects, while groups larger than 15 begin forming divisive subgroups. These 12 people represent carefully selected expertise. You need a medical doctor who can perform surgery if necessary, because medevac to Earth isn't an option. You need mechanical engineers who can repair anything from spacesuits to power systems. You need electrical engineers for troubleshooting circuits and software. You need geologists to analyze Martian terrain and locate resources. You need botanists for the eventual food production systems. You need someone trained in habitat construction and life support maintenance. But specialization has limits. Everyone cross-trains. The doctor learns basic mechanical repair. The engineers learn medical first aid. The geologist learns how to operate excavation equipment. On Mars, "That's not my job" is a death sentence. The crew functions on Mars, which introduces entirely new problems. Plants require water, which you have from ice extraction. They require carbon dioxide, which Mars provides abundantly in the atmosphere. They require nitrogen for proteins, which Mars has, but in limited quantities. They require light, which on Mars is 43% as intense as Earth, and dust storms can block it entirely. They require temperature control, because Martian surface temperatures swing wildly. And they require about 365 square meters of growing space per person to provide adequate nutrition. The first crew won't achieve full food self-sufficiency. That's unrealistic. But they'll establish proof-of-concept greenhouses, test which crops grow reliably in Martian conditions, debug irrigation systems, and gather data on growth rates. Leafy greens grow fast,
and provide fresh vitamins. Potatoes offer caloric density. Soybeans provide protein. Each successful harvest reduces future missions' dependence on Earth supply chains. Parallel to SpaceX's efforts, China has announced plans to send crews to Mars orbit by 2050, with surface missions to follow. The Chinese timeline is more conservative, but follows similar logic. Establish orbital infrastructure first. Use that as a staging point, then descend to the surface. China's Mars sample return mission, planned for 2028, demonstrates they're developing the landing and ascent technology required for crewed missions. This isn't competition in the Cold War sense, where secrecy and rivalry dominate. Both programs benefit from open publication of results. When SpaceX demonstrates that Starship heat shields survive Mars' atmospheric entry, Chinese engineers learn from that data. When Chinese rovers test novel regolith processing techniques, SpaceX engineers study the results. Mars is hard enough that everyone benefits from shared knowledge, even while maintaining separate programs. The European Space Agency and others receiving a response and replying. This asynchronous communication fundamentally alters social connection. Isolation studies from Antarctica give us some idea what to expect. Winter overcrews at research stations experience psychological stress from months of darkness, confinement, and limited social circles. Some handle it well. Others develop depression, anxiety, or interpersonal conflicts that would be minor annoyances in normal circumstances, but become intense in isolation. Mars crews will face similar pressures, multiplied by the knowledge that they cannot leave, even if things go badly. Selection and training try to minimize these risks. Candidates undergo extensive psychological screening. They train together for years before launch, building trust and understanding. They practice conflict resolution. They develop coping mechanisms for stress. But you can't fully prepare someone for 2 years on another planet. Some problems only emerge under actual conditions. The habitat design tries to accommodate psychological needs. Private sleeping quarters give everyone space for solitude. Common areas facilitate social interaction. Windows, even small ones, provide visual connection to the outside environment. Exercise equipment maintains physical and mental health. The habitat isn't a prison. It's a home, and that distinction matters. During their 2-year stay, the crew follows a structured but flexible schedule. Mars operates on a 24-hour and 37-minute day, slightly longer than Earth. The crew adopts Martian time, which means their schedule slowly drifts relative to Earth. This sounds minor, but affects communication scheduling and can disorient crew members whose circadian rhythms struggle to adapt. Daily activities include system maintenance, construction work, scientific research, exercise, meals, communication with Earth, and personal time. Unlike ISS crews who focus heavily on science, Mars Base Alpha crew focus primarily.
Mars Base Alpha expands. More habitats come online. Power generation increases. Propellant production scales up. The greenhouse area expands. Medical facilities improve. Communication infrastructure grows more robust. This second wave brings different expertise. The first crew were builders. The second wave includes more scientists, agricultural specialists, and people focused on establishing long-term operations rather than emergency survival. The psychology shifts from can we survive to how do we thrive. By 2036, the base might house 100 people across multiple habitat modules. This is where colony starts becoming accurate. 100 people is enough for social diversity, specialized roles, and the beginning of a real community rather than just a crew. People form friendships, relationships, rivalries. Culture begins to emerge, distinct from Earth culture, shaped by the unique constraints and opportunities of Martian life. But 100 people is nowhere near self-sufficient. They still depend heavily on supply missions from Earth. Every 2 years, cargo starships arrive during the transfer window, bringing spare parts, specialized equipment, medical supplies, and food supplements. The base produces perhaps 30% of its food needs, 70% of its water through recycling and extraction, and 100% of its propellant through local production. Oxygen production is close to self-sufficient. Carbon dioxide scrubbing from the atmosphere provides all they need. Musk stated in 2024 that achieving self-sufficiency would require 7 to 9 years of serious colonization effort. By 2036 or 2038, that timeline suggests Mars Base Alpha should reach the threshold where Earth supply disruptions wouldn't cause immediate collapse. They'd have enough stored food, robust enough systems, and sufficient local production to survive several years without new arrivals. This threshold represents the difference between an outpost and a colony with life support, because nothing else matters if people can't breathe. Earth's atmosphere is approximately 78% nitrogen, 21% oxygen, and trace gases including carbon dioxide at about 0.04%. Humans need oxygen to survive, but pure oxygen environments are dangerous. The Apollo 1 fire killed 3 astronauts in 1967 because their capsule used pure oxygen at high pressure, turning a minor electrical spark into an inferno. You need nitrogen or another inert gas to dilute oxygen and reduce fire risk. Mars's atmosphere is 95% carbon dioxide, 2.7% nitrogen, 1.6% argon, and only 0.13% oxygen. It's also extremely thin, with surface pressure averaging about 600 pascals, compared to Earth's 101,325 pascals. You can't breathe it. It won't hold heat. And exposure means rapid death from asphyxiation and depressurization. so habitats need closed-loop life support systems. The International Space Station provides a working model. ISS uses electrolysis to split water into hydrogen and oxygen. Crew breathes the oxygen. Carbon dioxide from exhalation is captured by scrubbers and processed through the Sabatier reaction to produce water and methane. The water gets recycled. The methane, unfortunately, is vented to space because ISS can't use it. On Mars, that methane becomes fuel. This creates an almost closed loop. Almost, because some losses occur. Water molecules escape through airlock cycling. Metabolic processes consume small amounts of hydrogen. You need periodic resupply, but a well-designed system can recycle perhaps 95% of water and oxygen indefinitely. That 5% loss is manageable through local resource extraction. Energy drives everything. On Earth, we take energy for granted. Flip a switch, lights come on. On Mars baseline, small modular reactors can generate continuous power regardless of dust, darkness, or weather. NASA has developed killer power reactors specifically for space applications, producing 1 to 10 kilowatts continuously for over 10 years without refueling. Scale that up to 100 kilowatt or even megawatt class reactors, and you have enough power to run a growing colony. The challenge is launching nuclear reactors into space. Public concern about launch failures spreading radioactive material creates political obstacles. But the actual risk is lower than commonly perceived. Modern reactor designs use low enriched uranium in forms that wouldn't disperse widely in a launch accident. Still, the optics matter. Early missions will likely rely primarily on solar with battery storage, accepting the limitations, while nuclear reactors arrive only after landing reliability is thoroughly proven. Water extraction is critical infrastructure. Mars has substantial water ice, particularly in polar regions and buried at various depths in mid-latitudes. Orbital radar has mapped these deposits extensively. Some locations have ice layers just centimeters below the surface. Others require drilling several meters. The extraction process is straightforward in principle. Excavate regolith containing ice. Heat it to melt the ice. Collect liquid water. Filter out contaminants, and pump to storage tanks. In practice, Martian soil is more challenging than it sounds. The regolith contains perchlorates, toxic compounds that must be filtered out. The ice is often mixed with soil rather than pure layers, requiring more heating energy. Temperatures drop so low that equipment must be heated continuously to prevent freezing. Water serves multiple purposes beyond drinking. Split through electrolysis, it produces hydrogen and oxygen. Oxygen supports respiration and serves as rocket oxidizer. Hydrogen feeds the Sabatier reaction to produce methane fuel. Water also provides radiation shielding. A habitat surrounded by water tanks benefits from excellent radiation available resources. The ISS already uses a small-scale Sabatier reactor as part of its life support system.
though it vents the methane produced rather than storing it. Mars systems will scale this up dramatically, processing tons of carbon dioxide per day to refuel starships over several months. The chemistry is proven. The engineering challenge is building reactors reliable enough to operate for years without maintenance in Martian conditions. Radiation protection is one of Mars's hardest challenges. Earth's magnetic field deflects most cosmic radiation and solar particle events. Mars lost its global magnetic field billions of years ago. Surface radiation exposure is roughly 100 times higher than Earth. Long-term exposure dramatically increases cancer risk. There are 3 approaches to radiation protection. First, shielding with mass. Thick walls of water, regolith, or other materials absorb high-energy particles. 3 meters of compacted regolith reduces radiation to near-Earth levels. This is why optimal habitat designs place living quarters underground or cover them with substantial regolith layers. Second, limiting exposure time. Spend minimal time on the surface, conduct necessary external work quickly, and return to shielded habitats. Third, potentially creating localized magnetic fields. Though this remains mostly theoretical and power-intensive, NASA has been researching advanced radiation shielding materials that might provide protection with less mass. Hydrogen-rich polymers show promise because hydrogen atoms are particularly effective at absorbing high-energy protons. Combining these materials with water shielding and regolith coverage provides layered protection. 3-dimensional printing using Martian materials offers construction flexibility without launching massive amounts of building supplies from Earth. Regolith-based concrete uses local dust mixed with small amounts of polymer or water as a binder. It's not as strong as Earth concrete, but it's adequate for habitat construction under Mars's lower gravity. Several designs have been tested. Gravity, as experienced on the ISS, causes well-documented problems. Astronauts lose bone density, muscle mass declines, vision changes occur, and immune function weakens. These effects reverse after returning to Earth, but they limit how long people can safely stay in microgravity. Mars's partial gravity might avoid these problems, or it might cause them at a slower rate. We simply don't know because no humans have ever lived in partial gravity for extended periods. Animal studies could provide answers, but they require actually going to Mars. You can't simulate Mars gravity on Earth except during brief parabolic flight maneuvers. The ISS can't help because it's microgravity. A rotating space station could create artificial gravity through centrifugal force, but none exist yet. So one of Mars colonization's biggest unknowns remains. Can humans thrive in 38% gravity, or will they face similar deterioration as in zero gravity? Food production closes the survival loop. Humans need approximately 2,000 calories per day, which requires growing substantial quantities of crops. Plants need light, water, carbon dioxide, nutrients, and appropriate temperature. Mars provides carbon dioxide abundantly. Water comes from ice extraction. But light is weaker, and growing plants indoors with artificial light is energy intensive. Approximately 365 square meters of growing space per person provides adequate nutrition using efficient crops. Leafy greens like lettuce and spinach grow quickly and provide vitamins, but limited calories. Potatoes offer higher caloric density in relatively compact growing area. Soybeans provide protein. Wheat provides carbohydrates. A diversified diet requires multiple crop varieties, each with different growing requirements. The energy calculation is daunting. Plants convert roughly 1% of light energy into edible biomass through photosynthesis. If you need 2,000 calories per person per day,
and testing. This is what makes the 2060 timeline credible. We're not speculating about breakthrough inventions that might never come. We're scaling up proven technologies and adapting them to Martian conditions. The difference between now and 50 years ago is cost and reliability. The Apollo program could have sent people to Mars in the 1980s if national will and unlimited budgets existed. But the cost would have been astronomical, and the mission would have been flags and footprints with no permanent presence. Today, reusable rockets, advanced life support, in-situ resource utilization, and decades of orbital operations experience make permanent settlement feasible rather than merely possible. Technology isn't the limiting factor anymore. Economics, politics, and human factors are the real challenges. But having the technology solved removes one enormous barrier. We know how to keep people alive on Mars. Now the question is whether we have the sustained commitment to actually do it for the decades required to establish permanent presence. Food is the problem that exposes every romantic notion about Mars colonization. You can compress life support into compact systems. You can shield habitats against radiation with regolith layers. You can extract water from ice and synthesize fuel from atmosphere. But food demands space, energy, time, and biological systems that resist simple engineering solutions. Growing food on Mars isn't just hard. It redefines what hard means. Start with the fundamental requirement. A human needs approximately 2,000 calories per day to maintain health and work capacity. That translates to roughly 1.5 kilograms of food daily, or about 550 kilograms annually per person. For a colony of 100 people, you're looking at 55,000 kilograms of food each year. For 1,000, storms are common and can last days or weeks. Global dust storms are rarer, occurring roughly every few Martian years, but they can shroud the entire planet for months. The 2018 global dust storm killed the Opportunity rover by blocking sunlight to its solar panels.
For a greenhouse depending on natural light, global dust storms mean months without adequate photosynthesis. Artificial lighting provides backup, but at enormous energy cost. Plants convert only about 0.5 to 1% of light energy into edible biomass through photosynthesis. If you need 2,000 calories per person per day, and only 1% of light energy becomes food, the power requirements become staggering. LED grow lights are more efficient than traditional lighting, but you're still looking at thousands of watts per person continuously, adding to the colony's already substantial power demands. Greenhouse design tries to maximize natural light while maintaining pressure and temperature. Transparent domes or inflatable structures made from strong polymers allow sunlight in while containing breathable atmosphere. But these structures face challenges. The polymer must withstand pressure differential, resist degradation from ultraviolet radiation, and remain transparent despite inevitable dust accumulation on exterior surfaces. Cleaning the exterior requires regular EVA activity, exposing workers to radiation and environmental hazards. Temperature control is critical. Mars's surface temperature averages -60 degrees Celsius, with extremes ranging from -125 at the poles in winter to 20 degrees Celsius at the equator in summer. Plants generally require temperatures between 15 and 30 degrees Celsius. The greenhouse must be heated continuously, which consumes energy. Insulation helps, but complicates the transparent structure design. Water is available from ice extraction, but distribution poses problems. Plants need consistent moisture without oversaturation. On Earth, soil microbiomes help regulate
Efficient crop varieties. In practice, you'll need more space to account for crop failures, experimentation with what grows best, and rotation to prevent soil nutrient depletion in hydroponic systems. Crop selection matters enormously. Leafy greens like lettuce, spinach, and kale grow quickly, provide vitamins and minerals, but offer limited calories. Potatoes provide excellent caloric density per square meter of growing space. Soybeans offer protein and oil. Wheat provides carbohydrates but requires more growing time. A balanced diet needs variety, which means managing multiple crop types with different growing requirements. The photosynthesis efficiency problem is unavoidable. Plants convert roughly 1% of light energy into edible calories. This means 99% of the energy you invest in lighting becomes heat rather than food. Even using natural sunlight, the space and infrastructure requirements are substantial. Transparent growing areas must be maintained, kept clean, pressurized, heated, and continuously monitored. Some researchers propose biological reactor systems that bypass traditional farming. Use bacteria or algae to convert carbon dioxide and hydrogen directly into proteins, fats, and carbohydrates. These systems could be more space efficient and faster than growing crops. NASA has funded research into these approaches, and some experimental systems exist. But there's a catch nobody likes to discuss. These foods taste terrible. Humans evolved eating complex plant and animal tissues with intricate flavor compounds. Food grown in bioreactors is nutritionally complete, but monotonous. Psychological research on isolated populations shows that food quality significantly affects morale and mental health. Eating nutritionally adequate but flavorless paste for years might meet biological needs while undermining psychological well-being. This is where hybrid approaches make sense. Grow some food conventionally for variety and morale. Supplement with efficient bioreactor systems for basic caloric needs. It's not purely optimal from an engineering standpoint, but humans aren't purely rational systems, incrementally more dependent on imports from Earth. Biosphere 2 taught us valuable lessons about closed ecosystems, mostly about what fails. In the early 1990s, researchers sealed 8 people inside a massive greenhouse complex in Arizona, attempting to create a self-sustaining ecosystem. Oxygen levels dropped unexpectedly as microbes in the soil consumed oxygen faster than plants produced it. Carbon dioxide levels fluctuated wildly. Food production fell short of requirements, and crew members lost substantial weight. The experiment revealed that closed ecosystems are far more complex and unstable than theoretical models suggest. Mars colonies can learn from these failures. Keep systems modular rather than trying to create one massive closed ecosystem. Use mechanical oxygen generation rather than depending purely on plant photosynthesis. Accept that perfect closure is impossible and plan for periodic resupply and adjustment. Design systems with multiple redundancies so that one failure doesn't cascade into collapse. The mass equation for food production systems adds another constraint. Growing systems, including structures, hydroponic equipment, water reservoirs, pumps, lighting, and backup systems, weigh approximately 7 times the food they produce annually. To feed 100 people, requiring 55,000 kilograms of food yearly, you need roughly 385,000 kilograms of agricultural infrastructure. That's 3,850 tons, requiring dozens of Starship cargo flights to establish. This is why robotic preparation is essential. Cargo starships arrive years before the first crew, delivering greenhouse materials, hydroponic systems, and agricultural equipment. Robots assemble structures, install systems, and test operations. By the time humans arrive, greenhouses are operational and initial crops are growing. The crew doesn't have to build everything from scratch while eating stored rations and race for higher photosynthetic efficiency under low-light conditions, or modified to grow in Martian regolith with minimal nutrient additions, could significantly improve yields. But genetic modification introduces its own complexities and potential unforeseen consequences. The harsh reality is this: food production on Mars will consume massive resources, require constant attention,
operate with thin margins for error, and still barely meet nutritional requirements for years or decades. It's not the dramatic challenge of landing on Mars or surviving radiation. It's the grinding daily challenge of keeping people fed. Miss a crop rotation because equipment fails during a dust storm, and the colony faces shortages. Contamination in hydroponic systems could wipe out entire food supplies. This is perhaps the most sobering aspect of Mars colonization. Space travel is spectacular. Rocket launches, orbital maneuvers, landing on new worlds. Food production is mundane. It's troubleshooting irrigation systems, adjusting nutrient concentrations, harvesting crops, processing waste, repeating endlessly. But without it, nothing else matters. You can't build a civilization without solving how to eat. The path to self-sufficiency runs through agriculture. When a Mars colony can reliably grow enough food to feed its population with minimal Earth support, it crosses the threshold from outpost to settlement. Until then, every starship that fails to arrive, every supply delay, every crop failure threatens survival. That vulnerability defines the difference between living on Mars and truly colonizing it. Every colony in human history faced the same question. What makes you economically viable? The answer determines whether a settlement thrives, survives on life support from the homeland, or collapses entirely. For Mars, this question is harder than any engineering challenge. You can't export
From Earth to orbit run roughly $10,000 per kilogram using reusable rockets. From Mars to Earth is less energy intensive due to lower Martian gravity, but you still face months of transit time, life support for crew or maintenance systems, and risk of mission failure. No mineral commodity justifies that cost structure. What about intellectual property? Maybe Mars becomes a hub for scientific research, and patents or discoveries generate revenue. This works marginally better than physical exports, but research funding depends on Earth institutions with Earth priorities. If political winds shift and Earth governments decide Mars research isn't worth funding, the colony faces economic collapse. Depending on research grants makes you a dependent outpost, not a self-sustaining colony. Tourism is frequently suggested. Rich people pay millions to visit Mars for adventure and bragging rights. This might generate some revenue during early phases, but tourism isn't a foundation for permanent civilization. Tourist economies on Earth work because tourists spend money, then leave, allowing locals to maintain normal life between visits. On Mars, with 26-month transfer windows, tourists would arrive, stay for 2 years because they can't leave sooner, and consume resources while contributing little. That's not tourism. That's immigration with extra steps. So if traditional exports don't work, what does? The answer lies in Mars's position in the solar system and what economists call comparative advantage. Mars isn't competing with Earth directly. It's serving as a keystone for expansion beyond Earth.
The asteroid belt lies between Mars and Jupiter, containing trillions of dollars worth of water, metals, and other resources. Accessing the asteroid belt from Earth requires enormous energy to climb out of Earth's gravity well. Accessing it from Mars requires less energy, because Martian gravity is only 38% of Earth's. Mars becomes the logical staging point for asteroid mining operations. Now the economics start making sense. You don't ship asteroid resources back to Earth necessarily, though some high-value materials might justify it. You ship them to Mars, where a return. Earth pours resources into Mars, getting nothing back except scientific data and symbolic achievement. But once Mars has substantial industrial capacity, propellant production, manufacturing capabilities, and a skilled workforce, it becomes cheaper to build and fuel spacecraft at Mars than launching them from Earth for asteroid belt operations. The labor economics matter too. Mars will face chronic labor shortages for decades. Building an entire civilization from scratch requires millions of person-hours of work. When labor is scarce, wages rise. Higher wages attract immigrants willing to endure harsh conditions for economic opportunity. This is how every frontier economy has worked, from the American West to Australian mining towns to Alaskan oil fields. People go to hard places when the economic return justifies the sacrifice. Offer someone on Earth double their current salary to spend 2 years on Mars, and you'll find takers. Offer triple salary plus debt forgiveness, and you'll have more applicants than positions. The economics become attractive once the colony is stable enough that people believe they'll survive the journey and return with their earnings intact. But this only works if Mars develops real economic productivity. If colonists arrive, work hard, but produce nothing of value because Mars remains dependent on Earth for everything, then wage premiums don't matter. The colony is a money pit, consuming resources without generating return. Self-sufficiency is the economic threshold that transforms Mars from charity project to viable economy. The economic viability timeline probably runs something like this. The 2030s are pure investment, establishing infrastructure with no expectation of return. The 2040s begin generating modest return as Mars provides services to early asteroid mining operations, primarily propellant production and equipment repair. The 2050s see Mars developing substantial manufacturing capacity, building spacecraft, producing complex equipment, and reducing dependence on Earth for everything except the most advanced technology.
Model is interesting here. The company funds Starship development partially through commercial satellite launches and NASA contracts, but Musk has stated he's personally committed to Mars regardless of immediate profitability. That kind of long-term commitment from a wealthy individual or corporation can bridge the gap between government funding cycles and eventual economic viability. But betting on one person's obsession is risky. What happens if Musk loses interest, dies, or SpaceX faces financial crisis? The program could stall. This is why broader economic justification matters. Mars colonization needs to make sense to enough people and institutions that it continues, even when individual champions disappear. The historical parallel here is the Transcontinental Railroad in America. It never made direct economic sense.
The construction costs exceeded realistic revenue projections. But the US government subsidized it anyway because they understood that connecting east and west coasts generated indirect benefits far exceeding direct returns. The railroad enabled settlement, agriculture, mining, and trade that wouldn't have existed otherwise. The total economic benefit dwarfed the construction cost, even though the railroad companies themselves often struggled financially. Mars colonization follows similar logic. The direct economic return is questionable. The indirect benefits of becoming a multi-planet species, advancing technology, inspiring education, and opening the solar system to development potentially justify the cost. But those benefits are diffuse and hard to quantify, making political support fragile. This is where international cooperation helps. If costs are shared among multiple nations, no single country bears the full burden. If benefits accrue to humanity broadly, rather than one nation specifically, the political case strengthens. But international cooperation introduces complexity, competing interests, and slower decision-making. There's no perfect solution. The harsh economic reality is this: Mars colonization requires sustained investment of trillions of dollars over decades, with no guarantee of return. The economics don't work in traditional business terms. They only work if you value species survival, scientific knowledge, and long-term expansion beyond Earth enough to
sometimes make these long-term investments and sometimes don't. Which path humanity chooses will determine whether 2060 is remembered as the year Mars became self-sufficient or the year we gave up. We've traced the path from 2026 robotic landings through 2050's expansion. Now the central question returns. Why 2060 specifically? What makes that year significant rather than 2040, 2080, or eventually? The answer lies in the convergence of 4 separate factors that align around 2060 to create conditions for genuine, self-sustaining colonization. First factor: technological maturity. The technologies required for Mars colonization exist today in early form. Starship flew in 2024. Life support systems operate on ISS. In-situ resource utilization has been demonstrated at small scale. But moving from laboratory proof of concept to reliable operational systems takes decades. By 2060, these technologies will have undergone 35 years of refinement, iteration, and scaling. That's enough time to work through the problems that only reveal themselves through actual use. Compare this to aviation history. The Wright brothers flew in 1903. Commercial passenger service began around 1914. But reliable, safe commercial aviation didn't emerge until the 1930s, roughly 30 years after first flight. It took decades to develop weather-resistant aircraft, reliable engines, navigation systems, and safety procedures. Mars colonization follows similar timelines. First flights in the 2020s, early outposts in the 2030s, reliable operation by the 2050s, maturity by 2060. Second factor: economic viability. We discussed in episode 7 why traditional colonial economics don't work for Mars. The path to viability runs through becoming the industrial hub for asteroid belt operations,
and developing sufficient local production that import dependence drops to manageable levels. This doesn't happen overnight. Building industrial capacity, civilization. You need doctors, engineers, teachers, farmers, manufacturers, and specialists in hundreds of fields. Below a certain population threshold, you can't maintain that specialization. Everyone becomes a generalist, struggling to keep systems functioning. Estimates for minimum viable population range from tens of thousands to hundreds of thousands, depending on assumptions about automation, AI assistance, and how much dependence on Earth is acceptable. The million-person figure Musk cites isn't arbitrary. It represents population large enough that Mars society becomes self-perpetuating, even if Earth support disappeared entirely. Reaching population milestones requires exponential growth. Starting from hundreds in 2040, reaching thousands by 2050, tens of thousands by 2055, and approaching hundreds of thousands by 2060. This growth rate requires hundreds of Starship flights during every 26-month launch window, which requires manufacturing Starships at aircraft production rates, which requires sustained investment and demand. The demographic composition matters too. A population of mostly middle-aged engineers might maintain systems, but won't create a sustainable society. You need children being born, educated and maturing into adults who've never known Earth. Multi-generational presence is what transforms a colony into a civilization. By 2060, the first children born on Mars in the early 2040s will be adults themselves, perhaps with children of their own. That generational continuity is essential. Fourth factor: political will and international dynamics. Space programs require sustained political support through changes in government, economic conditions, and public opinion. The International Space Station's environmental challenges and Mars colonization is complex and unpredictable. There's also the comparison with historical colonization timelines. European colonization of the Americas began with Christopher Columbus in 1492. The Jamestown settlement in 1607 struggled but survived. By the mid-1600s, substantial colonies existed. By 1776, nearly 300 years after Columbus, the colonies declared independence. That's a much longer timeline than the 35 years from 2025 to 2060. But the comparison isn't direct. European colonists found breathable air, drinkable water, and food sources in the Americas. Mars offers none of these naturally. The technological gulf between 1492 and today is incomparable. Modern engineering, computers, Automation and accumulated scientific knowledge might compress colonization timelines that took centuries into decades. Or the harshness of Mars might stretch them even longer. The role of private enterprise matters. SpaceX isn't constrained by government budget cycles or political pressures the way NASA is. Elon Musk has explicitly stated he's willing to devote his personal fortune to Mars colonization, regardless of profitability. That kind of focused, obsessive drive can accomplish things that bureaucratic organizations can't. But it's also fragile, dependent on one person's health, judgment, and continued interest. What if Musk dies or loses interest before 2060? SpaceX could continue under new leadership, or the vision could fade. History shows that transformative projects often depend on charismatic leaders. After those leaders die, momentum can collapse unless institutions become strong enough to continue independently. China's parallel timeline creates both competition and insurance. If SpaceX's program stalls, China's continued progress might revive Western programs through competitive pressure. If China's program encounters problems, Western programs provide continuity. Having multiple independent efforts increases the probability that at least one succeeds. There are uncertainties that could delay every surface habitats, rather than requiring underground construction. Breakthrough agricultural technologies could reduce growing space and energy requirements. New manufacturing techniques could enable local production of complex equipment sooner than expected. The 2060 timeline isn't fate. It's a projection based on current technology developing steadily, without major breakthroughs or catastrophic setbacks. That steady development assumption might be too optimistic or too pessimistic. We won't know which until we're living through the actual events. What we can say is that 2060 represents the earliest plausible year when Mars colonization reaches genuine self-sufficiency based on reasonable extrapolations from current capabilities. It's not the latest possible year, but the earliest credible one. Earlier dates, like 2040 or 2045, don't allow sufficient time for technology maturation, population growth, and infrastructure development. Later dates, like 2080 or 2100, are unnecessarily conservative given current progress. The convergence is what makes 2060 compelling. If only one factor aligned, the prediction would be weak. But when technology, economics, demographics, and politics all point toward the same approximate time frame through independent analysis, that convergence carries weight. It suggests we're identifying a real threshold, rather than picking an arbitrary date. We've mapped the technological path to Mars, outlined the economics, traced the population growth, and explained why 2060 represents the convergence point. But honesty requires acknowledging what we don't know. There are fundamental questions about Mars colonization that can't be answered through simulation, calculation, or theoretical modeling. They can only be answered by actually doing it, by actually living on Mars for decades, and observing what happens. The first and perhaps most consequential unknown: can humans reproduce successfully in 38% gravity?
Don't know and can't know without actual testing.
Animal studies on Earth can't replicate partial gravity except during brief parabolic flight maneuvers. The ISS operates in microgravity, not partial gravity. There's no way to test this question without going to Mars, or building a large rotating space station that generates artificial gravity. And no such station exists. Now add pregnancy and fetal development to the equation. Human fetuses develop in 1G, with bone growth, muscle formation, cardiovascular system, and neural development all occurring under Earth gravity's constant pull. What happens if that pull is 62% weaker? Do bones develop properly? Does the cardiovascular system develop adequate strength? Do neurological systems form correctly? We have zero data on this. No mammals have ever gestated and been born in partial gravity. Some fish and amphibian eggs were flown on the space shuttle and developed in microgravity, with mixed results showing some developmental abnormalities. But extrapolating from fish to humans across different gravity levels is scientifically indefensible. The first human pregnancy on Mars will be an experiment with no control group and irreversible consequences for the child. This creates profound ethical challenges. You can't get informed consent from a fetus. Parents can consent on behalf of their children for medical treatments, but those have expected benefits. What's the benefit to the child of being conceived and gestated in potentially harmful conditions? The only apparent benefit is their existence, which is philosophically complicated when that existence might come with serious health problems. Some argue this is no different from parents having children in dangerous earthly environments, poverty, war zones, or areas with poor healthcare. Others counter that those situations emerge from circumstance, while choosing to conceive on Mars despite unknown risks against Earth's stronger gravitational pull. Maybe these changes are reversible with intensive physical therapy. Or maybe they're permanent. The psychological sustainability question is equally uncertain. We have data from Antarctic winter rover crews, submarine deployments, and ISS missions. All show psychological stress from isolation, confinement, and limited social circles. But those are temporary situations. People endure hardship knowing they'll eventually return to normal life. Mars settlers, especially those born there, don't have that certainty. Does permanent isolation from Earth create deeper psychological problems than temporary deployment? Or does accepting Mars as permanent home actually make it psychologically healthier? Because you stop yearning for departure and start investing in making your current situation livable. Human psychology is complex and varies enormously between individuals. Some people thrive in isolation, others deteriorate rapidly. Selecting psychologically resilient colonists helps, but over generations, selection effects fade, and normal human psychological diversity emerges. Cultural drift is inevitable, but unpredictable. Mars colonists will develop their own language variants, social norms, values, and identity, distinct from Earth cultures. This is natural and probably healthy, but it complicates governance and relationship with Earth. When Mars culture diverges significantly from Earth culture, do they remain one civilization with geographic separation, or become genuinely distinct civilizations that happen to share biological heritage? The communication delay fundamentally alters social connection. You can't have a phone conversation with family on Earth. You record a message, transmit it, wait 4 to 24 minutes depending on orbital positions, receive a response. Human expansion. Some argue that any native Martian life, even microbial, represents a unique branch of biology worth preserving above human interests. Others argue that microbes don't have moral status comparable to human civilization, and that once we're confident no complex life exists, colonization should proceed. These aren't purely scientific questions, they're philosophical and ethical. Different value systems reach different conclusions. Terraforming Mars is sometimes suggested as an eventual goal, thickening the atmosphere, raising temperatures, potentially making the surface habitable without spacesuits. The technical challenges are enormous, potentially requiring centuries of effort, but even discussing terraforming raises ethical questions. Does Mars belong to humanity to modify as we wish? Or does the planet have intrinsic value that we should preserve? If terraforming would destroy geological features or potential evidence of past life, is that acceptable? These questions become more urgent as Mars population grows, and colonists have their own opinions that might differ from Earth ethicists and policymakers. Mars colonists living there for generations might support aggressive terraforming that improves their quality of life, while Earth populations might prefer preserving Mars in its natural state. Who decides? The legal and governance framework remains murky. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but allows their exploration and use. Commercial exploitation occupies a grey area. As Mars develops permanent population, current space law becomes inadequate. Do Mars colonists have self-determination rights? Can they declare independence? What legal jurisdiction applies to crimes committed on Mars? These aren't hypothetical questions that can wait. The first permanent settlers arrive in the 2030s, according to the timelines we've discussed. We need legal frameworks before disputes emerge, but international consensus on space law moves slowly, while technology and colonization plans advance rapidly. The economic model remains unproven. We outlined in episode 7 how Mars might become economic paths to viability that current models don't predict. The technology questions extend beyond what we've covered. Can we develop propulsion systems that reduce transit time from months to weeks? That would dramatically improve safety, reduce psychological stress, and make Mars more accessible. Nuclear thermal or fusion propulsion might achieve this, but both face technical and political obstacles. If transit times remain at 4 months indefinitely, that constrains how quickly Mars can grow and how much interaction occurs between Earth and Mars populations. Can we create more effective radiation shielding without requiring meters of regolith? Advanced materials might provide better protection with less mass, allowing surface habitats with windows and views, rather than forcing everyone underground. Quality of life on Mars depends partly on whether people can see the landscape or must live in buried tunnels. Can we solve the food production challenge more efficiently? Current projections require enormous growing areas and energy consumption. Breakthroughs in agricultural technology, whether through genetic modification, artificial photosynthesis, or entirely novel approaches, could make Mars food self-sufficiency achievable with smaller population and less infrastructure. The answer to, can humanity truly become a two-planet species, remains uncertain. We have the basic technology. We have plausible economic models. We have organizational structures and tentative timelines. What we don't have is proof that humans can thrive across multiple generations on another planet. Survive, possibly. Thrive, we don't know. There's a difference between those concepts. Survival means not dying, maintaining minimal population, preserving basic civilization. Thriving means growing, innovating, creating culture, experiencing well-being, and choosing to continue rather than enduring out of necessity. A Mars colony that survives but makes everyone miserable has effort, trillions of dollars, and accepting substantial risks. Historical examples show civilizations sometimes maintain long-term focus and sometimes abandon projects halfway. We've built cathedrals requiring centuries to complete. We've also left unfinished monuments to shifting priorities. The difference between 2060 becoming the year of Mars's first self-sufficient colony or the year we gave up is commitment. Not just financial and political commitment, but psychological and cultural commitment. Does humanity collectively believe strongly enough that becoming multiplanetary matters to continue through setbacks, failures, and the long periods when nothing dramatic happens? We're not asking if anymore. That question was resolved when SpaceX proved reusable rockets work, when Mars rovers confirmed accessible water ice, when life support systems demonstrated closed-loop viability. The technology exists or is clearly developing. The question now is when and how, which are questions of commitment, resources, and execution, rather than fundamental possibility. The 2060 timeline represents optimism tempered by realism. Optimism that technology continues advancing, that political will persists, that economic models work, and that humans prove adaptable enough. Realism that this takes decades, costs trillions, requires solving thousands of problems, and might not work as planned. What we're witnessing in 2025 is the beginning. Not the dramatic beginning with flags planted and speeches given, but the practical beginning, with hardware being built, missions being planned, and systems being tested. In 35 years, we'll know whether that beginning led to humanity's first permanent colony on another world. The uncertainty is uncomfortable, but honest. Anyone claiming certainty about Mars colonization is either lying or
Yet will be answered by those who actually go, who actually live there, who actually build the civilization we're discussing. They'll face problems we haven't anticipated and find solutions we can't predict. That's how exploration works. You chart the path as carefully as possible, then adjust as reality reveals itself. The next 35 years will be extraordinary regardless of outcome. We'll either watch humanity build its first extraterrestrial civilization, or we'll learn hard lessons about why that vision doesn't work. Both are valuable. Both advance understanding. The only failure would be not trying, not learning, not pushing against the boundaries that have confined humanity to one planet for our entire existence. That's what 2060 represents. Not a guarantee, but a target. Not certainty, but possibility. Not the end of the journey, but perhaps the end of the beginning.